Hey guys, right now we're going to talk about induction proofs which involve differentiation. This is by all means not the worst type of induction proof. For example, inequalities, they tend to be worse. Induction proofs which involve trig or binomial coefficients. It is usually the case that AAHL students, they have a strong background in calculus. They should, given that, as we all know, great portion of an IB math exam is composed of calculus. And we should definitely take into account the fact that we're still talking about induction proof, therefore the same 5 steps are still involved. The propositional function, the base case, inductive hypothesis, inductive step, and the conclusion. They're all going to show up. What's going to differ, of course, the 4th step will feel different if you compare it, for example, with an induction proof which involves inequalities. Also, proving the base case sounds a little bit different. However, the structure remains the same. Let's tackle these 2 examples and make sure that you're on the right track when solving induction proofs with derivatives. On the first example, what we have is this function right here, the natural log of 1 plus x, and we need to prove that the nth derivative of f, which is symbolized fn of x, is equal to -1 to the n minus 1 times n minus 1 factorial over 1 plus x to the n. Now, we're going to start like we always start, which is by writing our propositional function. We're proving that the nth derivative of f is equal to this. This is the exercise itself. Now, we're going to get to the base case using 2 different strategies. We're going to differentiate by using differentiation rules, meaning quotient, product, chain, whatever's required. And knowing that the derivative of ln of x is equal to 1 over x, and applying the chain rule here, we have the derivative of ln of 1 plus x as 1 over 1 plus x times the derivative of 1 plus x, which of course is equal to 1. Therefore, the derivative of f of x is equal to 1 over 1 plus x. Now let's check whether this formula works. So using p of n, what we have is the first derivative of f, which is of course f prime of x, that is equal to -1 to the 1 minus 1 to the 0th power times 0 factorial over 1 plus x to the first power. Knowing that -1 to the 0 is 1 and also 0 factorial is 1, we have 1 over 1 plus x again. Therefore, the base case holds. Now, getting to our P of k, which is the inductive hypothesis. This is pretty much rewriting P of n, but substituting n by k, just like any regular induction proof exercise. We are going to assume that the following statement is true for some positive integer k. And there we have it. This is our P of k. Now, what is P of k plus 1, which is the inductive step? Well, if we get to the right result, we should get for P of k plus 1 the following expression. And notice that what we are doing is replacing k by k plus 1 using P of k as a reference. And of course, you can simplify this to k factorial, which shows to us that the k plus 1th derivative of f of x should be this one. Now, but how do we get to this? We didn't prove anything up to this point. We're just rewriting P of k plus 1, taking into account what P of k is. Now, the process is, assuming that P of k is true, and this is an assumption that we're making, we're going to differentiate this, or more precisely this, using differentiation rules. So we're going to take this expression and differentiate it with respect to x using any rule that might be required. Now, what you're going to write is using the kth derivative of f and differentiating it with respect to x. What we have is d dx of this function here. Now, remember that this is the goal. The goal is to get here. The same rules for derivatives apply to this case. So for example, if you're differentiating a constant, it disappears. If it's the derivative of a constant times a function, you just move the constant outside the derivative. If there's power rule, you can drop the exponent, subtract it by 1. All these things still apply. And the first thing to notice is that -1 to the k minus 1 and k minus 1 factorial, these are just constants. Therefore, we can move them and multiply it by the derivative itself. given that we can simply differentiate 1 over 1 plus x to the k. Now, differentiating 1 over 1 plus x to the k is the same as differentiating 1 plus x to the negative k, given that we can move 1 plus x to the k to the numerator, flipping the sign of k. And why would we do that? Well, so we could use the power rule. So we're going to drop the negative k, multiply this by 1 plus x to the negative k minus 1. So we're subtracting the exponent by 1. And then using the chain rule, we're going to multiply by the derivative of the inside function, which in this case, of course, is just 1. So you don't even have to write it. Now, notice that this negative k is the same thing as k times negative 1. And we can combine these negative 1's, which will give us negative 1 to the k minus 1 plus 1, which, of course, is the same thing as negative 1 to the k. And we can combine k with k minus 1 factorial, giving us k factorial. So we have negative 1 to the k times k factorial times 1 plus x to the negative k minus 1. Now, if you want to flip this and move the 1 plus x to the denominator, remember that you can rewrite this term as 1 plus x to the negative k plus 1, which means that this is the same as 1 over 1 plus x to the positive k plus 1. So 1 over 1 plus x to the k plus 1. Therefore, our final answer is negative 1 to the k factorial, over 1 plus x to the k plus 1, which is exactly what we're trying to prove. We're trying to get to this expression, and we just did. And we're pretty much done. The only thing that we have left is to vomit the conclusion, which is that sentence that you always use. So given that p of 1 is true, and p of k plus 1 is true, whenever p of k is true for some positive integer k, by the principle of mathematical induction, p of n is true for all positive integers. And there you have it. This is the first example. We're gonna move to the second one now. It's gonna look similar, it's gonna feel similar, so hopefully you're gonna be much more comfortable with the second example. All right, so moving to the second example, the function that we have in this case is 1 over 1 plus x. And we need to prove that the nth derivative of f is given by negative 1 to the n times n factorial over 1 plus x to the n plus 1. A bit similar to the previous exercise, but a bit different as well. We're going to go through the same 5 steps, starting of course with the propositional function. By the end of this exercise, we need to prove that this is the nth derivative of f, or this formula gives you the nth derivative of f of x. Now onto the base case. We're going to start by differentiating f of x using differentiation rules. And given that we can write f of x as 1 plus x to the negative 1, we can simply apply the power rule combined with the chain rule, so that the derivative of 1 plus x to the negative 1 is negative 1 plus x to the negative 2, times the derivative of the inside function 1 plus x, which is, of course, just 1, giving us negative 1 over 1 plus x squared. Now let's check if it actually matches us using the formula of f in x, substituting 1 into n. So using our p of n, the first derivative of f with respect to x, which of course can be rewritten as f prime of x, is equal to negative 1 to the first power times 1 factorial over 1 plus x to the 1 plus 1. And by remembering that 1 factorial is just 1, is indeed equal to negative 1 over 1 plus x squared. Therefore, the base case holds. Now, as you know, our p of k, which is the inductive hypothesis, is formed by taking our p of n and substituting every n by k, giving us this expression for the kth derivative of f of x. Don't forget to write that you are assuming that this is true for some positive integer k. And let me just remove something that I forgot to remove. There you go. Now we're good to move to the fourth step, which is the inductive step, the fun step. We're going to do something similar to p of k, but replacing every k by k plus 1 now. which gives us this expression right here, which can of course be simplified to the following: f of k plus 1, or the k plus 1th derivative of f, is equal to negative 1 to the k plus 1 times k plus 1 factorial over 1 plus x to the power of k plus 2. Now the goal, as you know, is to get here. So this is the goal. Now how do we get to the goal? We're going to use the kth derivative of f, which is our assumption, our inductive hypothesis, and we're going to differentiate it with respect to x. So we're going to find d dx of this guy right here. Now, just to restate something that I stated before, if you're differentiating a constant, and these are indeed constants, over a function, you can just move the constants to be outside of this differentiation process, multiplying the derivative of what's remaining to the right, which is 1 over 1 plus x to the k plus 1. Now, knowing that 1 over 1 plus x to the k plus 1 can be rewritten as 1 plus x to the negative k plus 1, which by the way is the same as negative k minus 1, we can drop this exponent and subtract it by 1 over here. So negative k minus 1 minus 1. So we have negative 1 to the k factorial times, and notice that this is the same as negative k plus 1, which can also be rewritten as negative 1 times k plus 1, of course, times 1 plus x to the negative k minus 2. And let's simplify it even more. So negative 1 times negative 1 to the first power is equal to negative 1 to the k plus 1. K factorial times k plus 1 is the same as k plus 1 factorial. Remember the rule for factorials? I like to use numbers as examples. So for example, if you have 4 factorial, you have 4 times 3 times 2 times 1. And if you multiply it by the next integer, which in this case is equal to 5, which is representing this k plus 1 here, the next integer, what you get is 5 factorial. 5 times 4 times 3 times 2 times 1. And there you go. And we still have over here 1 plus x to the negative k minus 2. And we can, of course, do better than this. Let's rewrite negative k minus 2 as negative k plus 2 and move this 1 plus x to the denominator so we can replace this negative sign by a positive one. So we have a positive exponent, meaning that we're going to have a product by 1 plus x to the k plus 2. Now this is exactly what shows up in our p of k plus 1. Negative 1 to the k plus 1, k plus 1 factorial over 1 plus x to the k plus 2. If you want to write it in that format, you can as well, of course. And that's it, we're done. We just need to write the conclusion, which is the same thing. I just copied and pasted it right here because it's exactly the same as the previous exercise, and we're good to go.